Yeah. So, welcome to another of our monthly webinars. Today, I'm proud to introduce to you the spectacular Getty Orawo. She'll be taking us through Recursion Devinity, and she insisted she wanted to introduce herself, so I'll let her do that. Just a few precautions we take. Kindly mute your mic if you're not speaking, and just so you know, we will be recording the session for those who are not able to attend, and then we'll upload it on YouTube. You can share the event with your social networks. Getty, hi.
Hola.
Hi everyone. Okay, move now. All right, so it's quite a pleasure to be here. I'm usually the one organizing this stuff, usually the cameraman, and now I'm just on the spotlight, and it's actually an honor, so I'm looking forward to it. I'm going to share my screen in a few. I need this, so sorry, just 1 second. Okay. All right, so hopefully you can all see my screen. Can I just get an affirmation before I begin?
Yes, I can.
Okay, great. Then I guess we're good. So hi guys, I'm very anxious and very nervous about this session. So if at all I freeze or break down in the middle of all this, you guys should understand. I mean, this is among my first talks, and I wouldn't say I'm that proficient in Elixir, but we try. So I guess introductions are in order. I begged Chantel not to introduce me because she would give me some really big titles that you guys would set a bar that I probably wouldn't reach. But basically, I'm Getty. You can call me Getty Orawo. I am a software developer, currently working with a company based in Nairobi. It's called SoccerWatch. But SoccerWatch's main stack is Ruby, although I'm very obsessed with Elixir. I run a girls in tech program called Girls Get Kiki that is currently in Kenya, but planning to go maybe international in a few months or a few years to come. So when I'm not being boring or when I'm not coding, I'm busy watching reruns of Avengers and Transformers, mostly Transformers. I could rewatch those stuff like a million times. Like it never gets old. So I'm just going to kick it off. So we'll begin with this topic, and it's iteration. So in Elixir, we don't actually have loops. And when we talk about iteration, it basically means repeating a sequence of steps or a sequence of instructions. So when I talk about a sequence of instructions, I would relate this to finishing a cereal box. That's an example I could throw out to you guys. Could be a cereal box, could be any other box. It could be biscuits. I don't know what you guys like, but I'm going to use a cereal box because it's a good enough analogy. So when you wake up in the morning and you want to take your cereal, so what do you do first? Get the box, pour the cereal into a bowl, pour the milk, put sugar, get your spoon, eat it. So when the cereal is over and you need more, you're going to do the same processes from procedure 1, right? You're going to pour the cereal into the bowl and pour your milk, and it goes on and on and on. So basically that is iteration for me. So when it comes to comparing this to iteration and enumeration, enumeration is actually a word that I have seen get passed around more in computing than in a normal conversation. Like I've never been in a conversation with a friend and they tell me I want to enumerate this stuff. Like who says that? But I've had it in computing a lot, so it's a term that I guess devs use a lot. I would say it's very interchangeable with the term iteration, because when we talk about enumeration, we're talking about a collection. And when we talk about a collection, we're talking about going through a collection or manipulating a collection, or basically just reading elements that are in that collection. So I really hope we understand this concept of iteration before we actually get into it. So an enumerable. How I would describe an enumerable. So my main stack is Ruby, and I didn't even jump into Elixir. I was pushed into Elixir. I found myself in the deep end with Elixir, but it's quite fun. For enumerables, I first learned them in Ruby, and basically for me it was just a collection. So anytime I heard the word enumerable, I knew this was something that would carry one data type or more, and anything that is enumerable is something that we can actually look through, or something that we can actually go through, do something to the elements in that collection, or just read them. So I'm feeling there's some noise. I hope it's not distracting people. I'm not sure what that is, but I'll carry on because it's not distracting me. Sorry. Okay, so collections can hold more than one element, basically what I've just explained right now. Data types that implement the enumerable protocol. So when we talk about the enumerable protocol, we're talking about something that we can iterate through. So off the top of my head, when I think of examples of enumerables, the first thing that would come to my mind is a list. Second thing that will come to my mind is map.
There's one more webinar going on.
Sorry? Sorry, Sandesh, are you saying something? I guess not. Sorry about that. I'll take questions, I guess, at the end of this. There's some procedure that Elixir webinar follows where the presenter gets to present and then we ask questions at the end of it all. Sorry about that. So when I think of example of enumerables off the top of my head, I would think of a list, of a map, or of a tuple or a tuple. Not sure how people pronounce that, but basically that's it. So when you're talking about an enumerable, we're talking about a collection, and there are various examples of that. So there's the enum module in Elixir, and there's the stream module. I haven't quite worked with the stream module, but very, very often they have worked with the enum module. So these are the modules that actually implement the enumerable protocol. This only means that functions or algorithms that are in this modules are ones that we can actually apply to enumerables. So when I talk to apply to enumerables, it just means when I have a list and I want to perform something to this list, right? I can have any of the functions on the enum module. I can't talk much about the stream module because I haven't worked with it, but I'm sure about the enum module. So any of the functions on the enum module, or some of them might work for my list because it's actually an enumerable. So when you come to also the enum module, it's a set kind of protocol that the first argument is always the enumerable. So we can do a really quick Elixir. I'm not sure the right way to search for docs, but this is me on a daily. So there's all these functions here for the enum module. Sorry. Oh, I'm sorry. I'm only sharing one screen, but let me change that real quick. I guess now you can see. Can you see? Great. All right, so these are the functions for the enum module. So I was saying that they implement this enumerable protocol, and this only means that they work for enumerables or an enumerable data type. So when you go to even the first example, what I was saying is that the first parameter that is passed to them will always be an enumerable. I guess this works for all of them that are in this list. So the first thing that will always pass to them is the enumerable that we want to actually manipulate or read. All right, so I guess that's it. So basically for iterations, when we're doing iterations, like in my case, I would use my favorite iteration, which is filter. Let's look at filter on the inner module. So for this functions, these are functions that are already abstracted for us. When I talk about abstraction, this just means that there are some functionalities that were there before that could have done the same thing that this function does. It's just that it was all bundled into one function, and someone actually did this for us. And that's why I really appreciate the aspect of abstraction. So there are high-level abstractions. Most of these functions on the inner module that when you go and look at the filter function or go look at the sort function, these are basically things that have been abstracted. Yeah, these are functions that we use on a daily. Maybe if you are a beginner or a junior like me, you ought to think that these functions just work. But thing is, they just don't work. They are some specific algorithms that actually work behind all this, and we're about to see all that. So yeah, I'm bored of talking, so let's write some code. I'm just going to move to my interpreter. Wow. Okay, so you guys already know how live demos go, so I'm not even going to preach this to you. So if we happen to meet an iceberg, you guys just understand. We've done live demos before, and they never go good. So let's create a module. Apparently, all functions in Elixir usually have to work within a module. What am I going to call my module? Since I'm at the office, I'm going to call it Podii, due to my lack of creativity. And then we want probably a function that will say sum. I'm gonna use a reduce, right? So let's call it sums. I'm not sure if sum is a keyword in Elixir. Someone correct me if it is, but I'm just gonna use sums to be safe. And a list will pass a list L. So inside this sums, I want to call a function that actually sums up all the elements of the list that you've given it. So in my case, I'm going to start with the list and then pipe it to enum.reduce. Oh, sorry, I've written list. Someone is correcting me here. Thank you. So enum.reduce, and we pass it. Let's see how enum.reduce works. I mean, we have the docs here. I am never ashamed to look at the docs for some reason. So reduce. So enum.reduce, invokes func, which is a function for each element in the enumerable with the accumulator. So basically we have the accumulator. The first element of the enumerable is used as the initial value of the accumulator. So in our case, we can have an accumulator of, say, 0 or not. I guess that's an optional field. So we can just do enum.reduce and then our function. So it takes two parameters. Our anonymous function takes 2 parameters, and then in our case we're not multiplying but adding. So that's what we're going to do. So I'll take lack of creativity, x and y, and x and y. Kindly correct me if I'm wrong with the syntax. Okay, and we're gonna do x plus y. Good. If there's any errors, I guess we will sort them out, right?
The comma after Y.
The comma after Y. Oh, this is unnecessary. Okay, great. Thank you. All right. And perfect. So we have our module Podii, and we call it with sums. And in our case, we give it a list of, sorry about that. We give it a list of, let's say, one element. We expect one. We give it a list of 2 elements. It adds it up. Let's tempt it to that. So yeah, our iterator actually works. So I would like to try this with a complication like passing it a string, and let's see how Elixir handles this. So we get an error of a bad argument in an arithmetic expression. So we definitely can't add strings to integers. So we're going to add an extra step to our function that actually filters the list and actually first checks for numbers and adds the numbers only, right? So that's why I was going for filter. So if I do enum.filter, remember every function in the enum module always has the enumerable as the first parameter. So I'm gonna filter 1, 2, a string, and what other data type do we have? What other data type do we have? A map. That's true. Right. So when we filter, we have to pass it a function, and in our function, I want to tell it to only give me the elements that are numbers. So I'm just going to use let me just use an anonymous function of which syntax I know. So I'm going to ask if x is number. So I think there's an is number function. I'll just confirm. Is number. Yeah, that's a kernel function, and it takes. Perfect. So we're just going to ask if x is a number. So we're only going to filter the elements that are numbers. Let's see if this works for us. Is number. And we pass it x. I guess that should work. Great. So it only returns the elements that are our numbers. So we're going to edit this function of ours that we had here. Let me just open gedit so we can write our functions there. Our functions, yeah, there. So we can do def module. I had called it Podii. And I remember my function name was sums, and it took a list. So in this case, what we're going to do is we're going to filter the numbers first. So I'm going to pass list to, sorry, I'm going to pass list to enum. I am very lazy. I'm just going to copy this. All right, so take this part out and we should be good. And we're also going to pass the result that we get to enum.reduce, just so we can get cumulatively the addition of all the digits or the numbers or the integers in our collection. So, and that. We thank God for advanced editors. Great. So unless I have any syntax errors, there's only one way to find out. So I'm going to call Podii.sums. And then I'll see if it works for my simplest case. Undefined function enum.filter3 is undefined or private. Did you mean filter? Oh, wow. How did I not say that? All right, so this is filter, but this is, wait, what did I do here? So I was to filter and then reduce. Enum.reduce, I'm just going to write it again. So we already passed it that, and we'll have x and y, and then I'm going to pass it to x plus y. And I think that's okay. All right, so I'm going to call, let me just hide this. I'm going to call Podii.sums and call it with 1. I guess that's cool. 1 and 2 should give us 3. And then when I add a character that shouldn't be added with the rest, still gives us 3. So basically this is our iterator. So how an iterator works is it goes through every element in the list and performs whatever operations we've told it to do on our function. So like in this case, for filter, what it does is that it goes to 1, checks if this 1 is a number. If it isn't, discards it. If it is, keeps it. And then the list is also passed to the next function, which is a reduce function, and it just manipulates it by adding all the numbers like x plus y cumulatively. So I guess that's a good enough visual of how an iterator works. So we'll just go back to our slides. Sorry about that. Okay, so wait 1 second, let me present this again. So yeah, we've written some code on iteration. So iterating is really easy, and the fact, the reason why this is actually easy is because this is abstraction that has been done for us. These are functions that are already on documentations, and this only means someone out there has made our lives easier by actually doing this. So we didn't even break a sweat, but it worked, and we thank heavens for that. Abstraction makes complex functionalities simple. That is very, very self-explanatory. So we iterated through the list twice to fulfill this. If that makes sense, it's just what I've explained right now. So we pass the list to the filter, it filters. But do remember, it's the same list that we're passing to the next function. So we're kind of iterating the list twice to do different things. So this is this procedure that we're trying to make better. And now we move to recursion. So there's this saying that goes, to iterate is human and to recurse is divine. That's why I called my talk Recursion Divinity. It's divine for the various reasons that you will see after this, but this will make sense to you, I think, once we're done. So there's this fun tip that I need all of you to think it through for me. Cool. There's this fun tip that I need all of you to think it through for me. Recursion is a method where the solution to a problem depends on the solution to smaller instances of the same problem. I'm going to run that again. Recursion is a method where the solution to a problem depends on the solution to smaller instances of the problem. Now, it took me a while before I had the aha moment for this quote or for this phrase. So I'm going to leave it there for you guys to just ponder on it. And at the end of this, at least one of you will just explain to me what this actually means. All right, so an introduction to recursion. This is my favorite part. So recursion is just a way to solve problems with elegance and simplicity, and I promise that you will see this. So a recursive function is basically a function that keeps calling itself, right? So it calls itself until it meets some kind of condition that actually tells it to stop. So this involves passing around state. So unlike Ruby, I can talk about Ruby because I'm from Ruby. We would basically have objects and variables, and whenever you want to save state or do something like that, we would pass them to, we would change an object state or basically just pass something to a variable. But with Elixir, it's different because we have functions that actually pass around state. That's a very interesting way to look at it. So basically what we want to do right now is to have our iteration, the filter function that we've done, and together with the reduce function that we've done, and actually de-abstract it. By de-abstract, I just mean actually recreating the functions without actually using the functions that are on the inner module. So this is going to be fun and have a lot of errors. So I'm very open to your critics. All right, so this is what we had before. Let me just create another function. Or we can use the same one since I hate creating names. Oh, I'm really going to call a function tree Dexter. I'm really out of names, you people. So there needs to be a space there. So basically what we're going to do is have these two functions on, on the same, since we're creating a recursive function, I wouldn't see a need to create a recursive function for filter and create a recursive function for reduce. So what we're going to do is, because we're trying to optimize our first function, which is this, we're just going to try as much as possible and make it as simple as humanly possible. So first, what would I do first? So I would do a list. Dexter will take a list that has head and a tail, I guess. So what this does is that it just recalls itself. Since it's a recursive function, we can start with that. So let Dexter recall itself with t in this case. So if this is the only function that we had here and we passed our list, so what it would do, it would split this into the head, and the tail is usually a list of the other characters that are remaining after extracting the head. So if we pass this to Dexter, it will just be like some loop that keeps going on and on and on. So for us to prevent this, or for us to handle our situation, I'd like to copy this and have another function here. And this function is going to check if I'm going to add a guard clause to check if our head is actually a number. So h, do that and that, and then when our head is actually a number, we want to actually add the next result of the next head, of the next iteration, or the next function call, that is a number or an integer, to our head at this time. So at the end of this all, I'll definitely explain how this comes to play. So if we pass our list at this point, I think this should come before that. The reason why I'm saying this is because if we have this function before this one that actually has a guard clause, our match will always match with this function, and we'll never get to actually call this one. So let's start with this that has a guard clause and then revert to the next one. So this will actually work for our situation. This will work perfectly, because when we have a head that is an integer, it will always add this to, it will always cumulatively add this. And when it is not an integer, it will resort to this one, to this function head right here and call it with a tail. That just means it's going to discard the values that are not integers. So this will work for us for now. But there's the last and final step, that when we get to a point where the list actually has one value, our tail will be an empty list, and we do not know how to take care of that at that point. So we're just going to do, whenever we receive an empty list, let's just return 0 so that it doesn't affect any of our calculations here. So when we have the last thing on the list as 0, we'll have our 0 here, and this will add it to every other cumulative head that has been added to this function. So we ought to try this out on our console. Okay, so I'm going to call Podii.dexter and pass it my lists. Pass it my list that has 1, 2, 3, and a string and a map. Perfect, to get 6, because if we take the integers alone, if we take 3 plus 2 plus 1, that actually makes sense to us, right? So this is our optimized, not optimized as such. This, we have just recreated the two functions, the filter and the reduce, with this function over here. So this is what we call recursion. And in most functions that are in the inner module, you will find that whatever works behind, the power that actually works behind these functions is the recursiveness. So I guess we can carry on. Okay, so I've just explained. So how does our recursive function work? So our recursive function works like this. So whenever we have a list that has 1, 2, 3, and we have, say, 3 there, and a map. Let me place this map here so that we actually see what really happens. Okay, so if we have a list that sort of looks like this, and we are passing it to our Dexter function within the Podii module, so what happens on the first, this will iterate only once. Now, this is an optimization from our previous function. On our previous function, we'd have to run this for the filter on the list, and we'll have to iterate the same list for the reduce. But in this case, we're just iterating the list once and then passing it to the function, and the function gets called multiple times. So on the first iteration, our head is going to be 1 and our tail is going to be 2. 2, the map, the 3, and the string. This is going to be our tail, and our head is going to be 1. So is 1 a number? Yes, it's a number. So it's going to be called, so this is the function that's going to execute the first iteration. So our head will be 1 at this point. So we move to the next iteration, and 2 is our head. Since we're calling this with a tail, 2 will be our head in this case. And when we call 2, it is a number, so it's going to revert to the first function as well. So in this case, we'll have to be calling Dexter with the remaining, which is the tail, and plus 2 and plus 1. And on the third iteration, when it finds something that isn't a number, it's going to revert to this function, the second function head. And when it reverts to this, it does nothing really, but just recalls the function, but with the tail. So it literally assumes this character and recalls the function with the others. So this is how the recursion basically works. So at the end of the day, you will find that when we do this recursion, we will have gone like a number of iterations that is equal to whatever length our list is. So in this case, we will have called our function 1, 2, 3, 4, 5 5 times, but not forgetting the one time that we also call the function for the last call that has an empty list. Wow, this is so hard. Okay, so that's basically the explanation for that. So the function gets called the same number of times as the enum length, just what I've said, plus one more time for the final empty list. The final empty list is where we tell our recursive function to actually stop. So with each iteration, a stack frame is added to the call stack. So what exactly is a stack frame? I'm going to explain that. So when you talk about a call stack is a data structure that actually stores data about active functions in a computer program. So if you have any active functions, they're usually stored in a call stack. And this call stack usually has many stack frames. When you talk about a stack frame, it's just data to do with your function call at the time. So our function call in this case, our function call is Dexter. And for Dexter, we have the various arguments that we call it with, and these are the arguments. So what is stored on the stack frame is these arguments plus the function call. So now that we know what the stack frame is, with every iteration we call our function, we actually add a stack frame to the call stack. The call stack is where all this data is stored, and the stack frame is the data for our particular function at the time. So when we look at our function and how we iterate through 1 and 2 and the map and 3 and the string, whenever we call 1, we have to do a function call, which is Dexter, and we have to pass the following parameters. Whenever we call 2, we have to do the same. So for each and every iteration, a stack frame is usually added to the call stack, right? So this requires more memory use because, yeah, for the stack, and it could cause an overhead. So what we mean by an overhead is just an excessive use of memory or computing time. Yeah. So could we possibly optimize our function more from here? I honestly have no idea, but we can check out our last result and then see which works best for us. So up to there, I hope we are still on the same page. If I'm talking too fast, I'm sorry, it's because I'm nervous, but I hope I'm doing good. So we go to our file, and I already called the body recursion my favorite part, so I can't call this my favorite. So my favorite part. So for tail recursion, it keeps the memory footprint to a minimum. Like the way we've been ranting about memory when we talk about a stack frame getting added to the call stack every time we iterate through the function. This is just to make our function better. So just a small refactor to our code can prevent this stack frames from being added. So this only means less memory use, and I think that's a good thing. So what we can do is we can do a really minor edit to our recursive function to make it more optimized. Hey, you guys, presenting is hard. After this, I'm going to respect everyone who presents here. So we're going to just add a simple accumulator to our function calls. So I'll add one function over here, a function that is definitely not called Dexter, one that you can actually call on our console. So let me call it addition. That is sane enough. So addition will be taking our list, because once we add an accumulator to our Dexter, we wouldn't quite expect someone who wants to add a few stuff on the list to also pass us an accumulator. That wouldn't make sense. So all we expect from the user or from the client is a list. And so what we do in our function here, we call Dexter with our list and the accumulator that we need. Right? The accumulator will begin from 0, and the accumulator is just to keep the current values that we have. So we will do, for every call to Dexter, we will add an accumulator. We will add an accumulator. So instead of that, we'll add an accumulator here as well. And here as well. And here. And lastly there. So since our accumulator will always be storing our current state, right? We do not particularly need to return 0 at this point because it's a literal, and the fact that we have our accumulator getting passed to the same function, we can just return our accumulator at this point. I hope that makes sense. So basically, our function will be working in the same way, but the one minor change that we've made is we are keeping state, or we are keeping track of our current value at every point or at every call, right? So at every call of the Dexter function, we are keeping track of our current or of our previous calculation. Sorry about that noise. All right, so we ought to try this out before I feel confident about it working. Okay, so we'll call Podii dot addition in this case and not Dexter. So let's see if it works the same for us. So that returns 0. That's an okay one. What's 7 plus 8 should give us 15. So we are good. There is not much of a difference from what we are seeing on our previous function that we had done, on our recursive function that we had done, plus the one that we have added an accumulator. But there is a significant cost for this, and I'm going to explain this to you. So how does our tail recursion function work? So we've already made a tiny edit to this. And so what happens is for every call to Dexter is our accumulator stores the current value. It's basically what I've just explained. Our accumulator stores the previous value, and now we can use it here. I want you guys to just see the importance for doing all this. So the importance for doing this tail recursion, and it's some kind of optimization, it doesn't really need to await a call to itself. So when we're doing this initially, I had told you that we have to call Dexter for every iteration, right? Because we are depending on the iteration of our list. But in this case, we've actually stored the previous value on our accumulator, so we don't necessarily need to await the function call. And that's a good thing. So it keeps an accumulator that stores the current value, just as we've seen. So instead, it doesn't stack function calls. And this is the best thing about this. For our previous function, we were using, for every stack frame that had carried the function call together with the arguments. In this case, we don't have to do multiple stack frames, and I'm explaining this here. So this is a snippet of a phrase that I caught somewhere, and it explained this better than I could have ever explained it. So by calling itself at the end of the function and passing the accumulator with the calculated values, the alarm virtual machine can execute a trick called the tail call optimization. So this allows it to circumvent or avoid adding a new stack frame. Instead, it uses the current frame by jumping back up to the beginning of the function. So we have, in a way, kind of tricked our stack to thinking that we're using the same stack frame. As much as we're still calling the function multiple times because it is a recursive function, but it has the illusion that we are actually using just one stack frame, but with different arguments. So in a nutshell, tail call optimization allows functions to call themselves without running into stack issues. So running into stack issues may be stuff like overhead that I've talked about, and this may be stuff like running out of memory or too much computing time or something like that. So the question is tail recursion always the way to go? I would pass that to you guys, but I'm going to explain something just real quick. You shouldn't be convinced, that tail recursion is always as efficient or more efficient than any other algorithm, because there are times or there are instances that body recursive functions can also be faster. This is when we're talking about doing something like mapping through a list that at the end returns a list. It takes a function that takes a list and returns a list. We have seen the tail call optimization actually work for us when we have a function that reduces. So we can always do a research and find out if this is really the best or the most efficient way. So there's this link that I had put here, and we need to take a look at it first. Wait, why can't I copy this? Okay. So this is a link to the 5, are they 5 or is it 7? The 7 myths of Erlang performance. And as you can see, the first myth states that tail recursive functions are much faster than recursive functions. This is not precisely true, and I'm just going to read this to you. According to the myth, using a tail recursive function that builds a list in reverse followed by a call to lists reverse is faster than a body recursive function that builds the list in correct order. The reason being that body recursive functions use more memory than tail recursive functions. As we've seen as we've seen the stack frame getting added multiple times, you can compare that to tail recursion, where we're only manipulating, or the Erlang virtual machine is actually making an illusion to the stack and telling it we're only using one frame at a time. So that was true to some extent before R12b. It was even more true before R7b. I honestly do not know what these are, but we will read through. Today, not so much. A body recursive function generally uses the same amount of memory as a tail recursive function. It is generally not possible to predict whether the tail recursive or the body recursive function will be faster. Therefore, use the version that makes your code cleaner. Hint, it is usually the body recursive function. So basically, there are instances where the tail recursion will work for you, and there are instances that body recursion will work for you. So there has been a lot of debates on no, body recursion is better, no, tail recursion will always beat body recursion, but I would refer to the Erlang docs, and all they say is that just use the version that makes your code cleaner. And I think that's all. So I hope I have done okay. And I guess that's the end of my talk. And it's been great presenting. I'll take questions if there are any. Please don't make them hard. Chantal? Thank you, guys.
Take questions. Anyone? Okay, then at least tell us you've learned something.
I'm looking for my haters. Is there anyone in the crowd who has an answer to this? Let me post it on the chat. Great presentation, thank you. All right, I just posted that on the chat. Is there anyone confident enough to explain this? Recursion is a method where the solution to a problem depends on the solution to smaller instances of the same problem. Also, if it doesn't make sense, it's okay to challenge it. It's someone's opinion, so. Anyone? Come on, people.
I can try.
Sure.
So the logic here is that let's say I've tried something on the chart. So
Okay.
assuming that I have an array of 1, 2, 3, and 4, the logic of recursion is that I'm only going to be solving chunks of it, and then with those chunks, I'm going to be adding them together. So for the first chunk, let's say I'm going to be starting with, I'm going to be I'm going to break the item into, let's assume, the head and the tail, okay? So I'm going to be solving for solving for the tail until I get back to the head. So I'm going to be doing 4 plus 3. So I'm going to be breaking let's see. I have the 1, 2, and 3, and 4. And then the next one, the first one should be, the first solution I'm going to be doing for is going to be for the 4 and 3. And then from the solution that I'm going to have, from the addition that I'm going to have from the 4 and 3, I'm going to add that to 2. And then later on, I'm going to add that to the 1.
That makes all the sense in the world. That makes sense. Thank you very much. Does anyone else want to give it a try? I think Breimer has explained it really good. So it's basically solving small chunks of a bigger problem, but the small chunks that you're actually solving help you solve the bigger chunks of the problem. Wow. The number of times I've used the word chunk. Guys, I am done. Thank you. This has been awesome. Chantal, back to you.
Thanks, Getty. It's been divine learning recursion. So yeah, we owe many thanks to you for coming today. I've learned a lot.
Thank you. Thank you.
And bye.
Thank you, guys. We'll see you guys on the next one. Thank you.